So today I'm going to talk about one research paper and just give you the walkthrough about a research paper called Lazy LLM, and which has been created by Apple with the contribution of Meta AI. And in this research paper, there is a two verticals, majorly two verticals are there called pre-filling stage and decoding stage. So in pre-filling stage, there is something called KV cache. I will talk more in detail. So what is KV cache, what all those things I will try to explain. But as of now, just try to understand in any kind of before getting understand about this lazy LLM, I would like to talk about why it needed. Okay. For any kind of LLM, there is a two vertical. Okay. There is a major drawback is like context window. So let's suppose you ask a question. There is some certain limit called input and output token limit. Okay. So if you will ask a question and the question is bigger, in that case, you will get a output input token limit error, like you exhausted your token. Similarly, if you ask a question that input is less, but when it generate the output and it exhausted their output token, then you will get an error called output token limit error, right? So these are the major challenge, and many techniques came into the picture prior to this research paper as well, but everything got failed, like meme GPT and all those things. So this whole agenda of reading this research paper without fine tuning, you can get your appropriate result. Okay, so that is the complete agenda of this research paper. And in this research paper, as I mentioned, there is a two vertical called pre-filling stage. And in pre-filling stage, we are just whenever we are means whenever we are asking any question in that, every token is not important to get the output. So we will try to get the optimal way how we can do that, right? How we can remove those unnecessary token which is not needed. So those are the things we will try to understand. And also I will talk about in the decoding stage how the KV cache work. Okay, so those are the things is there in the agenda. So, and without getting delay, let's jump into the KV cache section, how the KV cache section works. Show you how the KV cache work here. So if you will see in this presentation, let me show you. Before starting the KV cache, before KV cache also, I just wanted to talk about few things. How the self-attention work. It's a very basic component of transformer. So let's suppose I gave a sentence called the cat is on a chair. Before calculating the attention, we are converting into tokenize and tokens, and each word is getting, each word like the cat is on, every word is getting represented by the vector, and the vector size depends on the what kind of tokenizers you are using. So if you'll see, I'm using 4096, means each word is getting represented by the 4096 numbers vectors. And as there is a six word, that's what 6 cross 6 comma 4096, this is called q matrix. Okay. Similarly, if you will come at the KT matrix, is KT matrix is nothing but is the transpose of Q matrix. As Q matrix is 6,4096, then as Q is a 6,4096, then KT will be ultimately 4096 cross 6. And if you will do the multiplication of these things, means vector multiplication, matrix multiplication, you can see 4096 4096 will get cancelled, and the final output you will get 6 cross 6. Okay, and then this is something called matrix multiplication, and this formula I'm capturing from the attention that all you need research paper. And if you can see, there is formula also I have been captured, like attention that all you need, and where Q cross KT divided by dimension of K. Dimension of K means like what is your vector size, whatever tokenization techniques you are using, called square root of 4096. And if you will do this all this calculation, you will get some result, and this you can consider these all the values randomly picked. Okay, and so this formula you can consider this is just I am taking from the attention that all you need research paper. Okay, so if you'll do this, divide all those things, it's a scalar division. After vector multiplication, it's a scalar division. You will get some numbers with the के respect में the cat के respect में, and you will get the final output 6 cross 6. This is called all values are randomly. Okay. Now coming to that, we are applying the causal masking. Causal masking is what? Causal masking is nothing but we are giving the attention on the words and means on the word and the past word. The future word, we are just ignoring those things. So if you can see, if I'm considering the, we are giving the value of the, and remaining future words, we are making minus in front. Similarly, if I'm considering cat, then cat and the previous word, but is on a chair is getting valid as a minus infinitive. Similarly, is, if I'm considering is, then the cat is we are giving, and future words are same like a minus infinitive. Likewise, I did it for all those things for on and all those things. Now let's apply the sliding window. If you will see, we are adding the dot product in the previous slide. Now sliding window, let's suppose I'm considering chair. Chair is no dependencies with the, right? So chair might be dependent on the on, right? So we are giving the sliding window as a 3. So 3 word is, it will consider, remaining word it will mask out. Okay, mask means hide it out. So that vector multiplication will be less in this computation, and calculation will be less. So that's what we are doing. This is called applying the sliding window. After causal masking, we are applying that, and this concept came from the Mixtral. Okay, it was not a concept of transformer. It's just came from the Mixtral research paper, and that I incorporated here. So sliding window they applied, and the major, if you will see, the major drawback of this sliding window, you might understand, the reduce the number of dot product in the perform. This is the advantage, and thus the performance during the training and inferencing got increased. But there is, at the same time, you have to consider this limitation as well. The sliding window attention may lead to degradation performance of the model as some of the interactions. If you see, chair has, there is no dependencies with the. So chair might not able to understand the context of the. So it might be possible you will lose some interactions between the tokens, right? So that's the one thing. Okay, but I will tell you this is not happening at all. Okay, but sliding window attention can still allow one token, watch token outside of the window using the reasoning similar to the receptive field. If you'll see, this came from the CNN architecture. And if you'll see, I'm considering this sliding window at the very first section 3x3, and from 3x3 we captured only one, right? And if you will come to that, the receptive network, the last network of at the end, every network are internally connected, right? Every network will be internally connected to each other. Okay, so that's a thing. It is like even the chair, even if you can consider it as a chair, chair is not able to connect the, but ultimately on is connected with the. So likewise, and similarly, we are going to multiply with the V matrix, and V matrix is the similar size of input matrix. If you will do the multiplication at the end, you will get the output same as the input size. What was the input size? 6 cross 4096. And here also you are getting 6 cross 4096. Only difference, see, as we pass the input as the same size, output is also same size. But only difference, what is the difference in that case? Only difference, each token is aware about each other. That's the thing. Now let's talk about next token prediction task. Imagine we want to train a model, write a poem, okay, for this, and if you, it will create this kind of poem, right? So what is the, like, if I'll ask the poem on any kind of topic, it will generate the poem. That's fine. But up to what instant it will generate? Until unless there is some special token, it will not identify. In this case, called end of statement, right? End of statement token generated, then means LLM will get stop at that moment only. So let's see how the inferencing is working and how the KV-Cache help here. Okay, so let's suppose SOS means start of statement. I asked, then it predicted next word, love. Start of in love. If I'll pass love, then it will generate that. If I'll pass, okay, so let me generate that. So this is inference one. If I'll pass love, it generated that. And similarly, if I'll pass that, it will generate can quickly size like this. If I pass hurt, it generated end of statement. As soon as end of statement got generated, LLM will stop at that moment only, and it will not do the further inferencing. But if you'll see, every time our main agenda is what? To generate the end of statement. To generate the end of statement, we are loading complete word. If you'll see love, that, can, quickly, also we are loading every inference. In every inference we are, so it is unnecessary to unnecessary what we call unnecessary memory consumption. As we know, these are the things already aware about the model, then why we are loading these things while inferencing? We can keep inside of cache and we can load these things. That's what KV-Cache came into the picture. Okay, so let's see, in inference 3 we are passing love, that, can. Okay, what is the use of can? Because already model aware about that what we generated, why we are unnecessarily loading this. Similarly, like at the end is what we have to generate our end of statement, right? So that's the thing. So that's what the KV-Cache came into the picture, and let me show you how the KV-Cache can help here. So So here is the question, like, is there a way to make the model do less computation on token, and it has already seen during the inferencing? Then answer is yes. The solution is KV Cache. And let's talk about how the KV Cache can help to next token prediction without loading in earlier predicted token. Okay, so that's the thing we are going to talk about. And then from here we will start our lazy LLM. This KV Cache only help at the inference time. Inference may we can reduce the time. But what about the training? I will talk about that. So you can see here in this case, I took the sentence called 90496, means in the sentence 9 word. And similarly, if I'll consider KT, it will be just transpose of the Q matrix. So 4096, 9. If I'll do the multiplication, you will see 9 cross 9 because 4096. If you'll multiply with V vector, you will get the this call. This is the simple self attention. And from there, we are calculating the attention by using this below attention that all you need formula. Okay. So at the end, we will get the output. That's the thing. We got the output. Now, let me show you. This is the conventional machine transformer. Now, how the self attention during the next token prediction. This the first token came and the QT matrix calculator, and we got the result QKT. Similarly, second token, second QKT. So, and if you'll see here, 4 we consider, and at the end you can see QKT. If we are considering sliding window, we are not bothered about the previously calculated dot product. Why we are necessary? We are only interested in the last row, right? Because end of statement. So that's what we are going to remove those calculation, and we are capturing only the last token. So if you'll see the second token, third token came, then it calculated 3 cross 3. Fourth token came, 4 cross 4. It calculated. Okay, at inference 4. Now, if you'll see the vector multiplication we are doing, and we already computed this dot product in the previous step. So can we cache them? So yes, answer is that. Since the model causal, we don't care about the attention token in with the successor, but only with the token before it. Okay, so we are only considering the token just before it. Okay, so that's a agenda. And we don't care about these things. We want to predict the next token. We already predicted the previous one, so we are not going to load these things. After multiplying, we are just considering output token, which is called end of statement token. Output token 4 is nothing but it's our end of statement. We are just discarding these things, so that computation will be less comparatively, and inference will be very faster. This is all about the KV Cache. So yeah, so now we'll jump into our main agenda called lazy LLM. Okay, so but feel free, let me know in case if you think something you want to know more about the self attention or KV Cache or rolling buffer, any kind of topic over the comment. I'll make a separate video, but the agenda of this video is not to explain the KV Cache and all those things. The agenda is to make you understand about the research paper called lazy LLM. Okay, so lazy LLM, that's what I just gave you the brief introduction how the KV Cache and self attention work, right? So that's what that's what this complete introduction was. That now let me show you. Let me jump into the lazy LLM research paper. As I already mentioned, there is a two-part called pre-filling stage and decoding stage we talked about. And we also talked about the extensive experiment on the standard data set across the various tasks demonstrate lazy LLM to generate the method and to calculate the first token to predict. So if you ask any question to your chat GPT, once the response got calculated, right? Let me show you. If you'll ask who is the Prime Minister of India, it will take first 2 to 3 seconds. After generating the response, it will not stop at that moment. So that's called first token prediction time to take the first token prediction, right? So without fine tuning, we can get so the thing is that how to get earlier, as soon as earlier as that first token to predict the next token. That's important, because if you'll pass the 1,000 token, it might be possible only 30% or 20% token is needed to predict the next token. Unnecessary 70% token we are loading in the memory. So that's what. So as and you can see we referred the time take during the pre-filling stage, time to first token. This is called TTFT, means we have to reduce this time. Means any kind of LLM is only taking this much time to predict the first token to get the answer, right? And once the first token has been predicted, next token will be very smoother. but only problem is how to calculate, how to get the optimal first token. That optimal first token, predicting the that optimal first token is a time consuming process, right? So this author tried with the llama 2, and author tried with the some other accept model LLM, different LLM as well, and they identified that performance also got increased drastically, and the accuracy also got increased. The speed up also got increased, and accuracy also got increased. So during the pre-filling stage, we are just considering how we can reduce this time to first token prediction. Once your first token prediction has been done, then LLM will generate automatically. And how the things is work, let me explain that part. Means first token, how to calculate which token is important, which are token are important to predict, and which are token is not important, so that we can prune means we can remove those tokens, right? So that's a thing. So let me explain this part. So you can here, if you will see in this, at the KV cache, we have a empty cache first, and we got the input called lazy LLM is the training free token pruning techniques to improve the LLM inference with till with. And now in the next iteration, we are giving negligible. And same thing we loaded into the KV cache, and negligible we will add in the next iteration. Similarly, in next iteration, next word will get predicted called performance. So each time we are not loading inside of RAM, we are storing inside of KV cache, and we are just adding these things in the cache whenever next token got predicted. So if you'll see pre-filling and decoding for long prompt, with first token generation during the pre-filling stage could be slow. So if you'll see, on average time to generate the first token required 21 wall time to each sequence decoding step, account 23% of the total generation time in the long range runs. So you can see the first token prediction is only taking much time. Afterwards, the speed is very fast, right? So let's calculate. And if you will see, before that also many approach came into the picture. It's not about this is the very first time they bring this up. Many other related work also researchers did before this Apple and Meta AI lazy LLM. Other techniques also came into the picture. If you can see related work, right, inside of related work, there is many people tried to do lot of things. Okay, so so investigating how the TTFT can be improved given static transfer architecture within the line of research. So that's a whole agenda of this research paper, right? How we can improve this TTFT, means how we can reduce the TTFT, right? So if you'll see, there is a very first related work came called efficient long context inferencing. And if you'll see, very first token, if you can see this graph in the this very first token, once first token prediction is taking much time. Afterwards, the next token prediction is not taking this much of time. So that's the thing is showing here. So how we can remove those restriction to predict the first token, unnecessary token, right? Those unnecessary token from the input token, how we can remove those input token which is not necessary to predict the next token, so that inferencing, so that next token prediction will be very fast. Okay, then another technique called token pruning. Token pruning may average, like randomly they are going to remove some of the unnecessary token, and then they are going to again, the first token prediction got started quickly, but the thing is that performance was not up to them. I'll show you the benchmark. Then lazy LLM came into the picture. How the lazy LLM compute? Okay, so if you can see the lazy LLM, lazy LLM, instead of computing everything upfront, lazy LLM start by only calculating the necessary part. It's begin pruning token and deciding which are the less important right from the first step and generating the next, right? If you'll see this example, lazy LLM training free token pruning techniques is to improve LLM inference with negligible. This is the word we are going to predict, right? To predict next performance word, it might be possible some of the word is not needed here in this sentence. So you can see in the conventional LLM, this is an example of conventional LLM, lazy LLM training token, entire thing we are giving. So you see, this is the conventional LLM, how it does. But how lazy LLM does the same job? Lazy LLM, lazy LLM will is the training free token pruning techniques and improve the inference with negligible. And you can see only few of the word it considered to inference to predict negligible. Similarly, second iteration, if you have to predict the performance, it is not considering the entire words. It's just considering, see, lazy LLM, improve LLM inference with negligible. So now you similarly in the next iteration, again, it is speaking some of the words, not entire. Now the question might be, how you can ensure which word is the important. That's the whole agenda of this research paper, and that's what author came up with this calculation, this mathematical formula. How you can calculate, how you can find it out which token or which word is important to predict the next token. So this is the only challenge. So how they are going to calculate? So here is the mathematical formula, which tokens are important. To address lazy LLM used an idea inspired by the early exciting, which suggests that a token pass through the different layer of the model and their importance become clearer. Here is how it works, like called attention map. In each layer of the model has the attention map, which shows how much attention each token gives to every other token. This is represented by, you can see AL. This is represented by AL. AL means layer of Lth layer of the model, how much attention they are adding, means each token, how much attention they are adding the value in layer L. Okay, so here is the AH. If you can see, this is the neural network, basic neural network, and this is called input layer, this is called hidden layer. If you will pass the input in hidden layer, how much information got extracted, or how much importance the tokens are adding the value in this layer L. Okay, that's the thing. And how the calculation is getting done here, you can see for each token TI, they calculate the importance score called SI. Okay, SI is the importance at the ith layer, and this score is the average attention that all the attention head in the layer give to the token TI. Okay, so that's what they calculated. And H is what heads, means any LLM have their heads, like what are the things they can do, that's called head. A is nothing but attention, amount of attention, and S is what significant value, like how much value that tokens is adding in that particular layer. That's the thing. This is the simple formula they came up with it, and with that they are calculating like what are the neurons, what are the tokens are important to predict the next token, right? So if you'll see, so if you want to consider this as a example, in that way you can consider in that way, like okay, whenever we are going to write any kind of story or something, we are considering some hidden things, like hidden characters as well, and which is going to store inside of sticky note or something. Okay. Now let me show you few things. So yes, so in this case, you can see we remove some of the token, but it might be possible in next word prediction, whatever things we removed with the first layer, it could be needed, right, in the next token prediction. So in this case, we are not removing entirely. We are storing somewhere, which is called aux cache. I will talk about. See, this is the complete sentence. And here we remove 30%. In next iteration, we are removing another 30%. In another iteration, we are removing 30%. But it might be possible in the, let's suppose in the last iteration, we needed some of the tokens, which we removed at the very early stage. How we can retrieve that? So lazy LLM came up with the another concept called aux cache. So whatever things we are removing, we are not removing entirely from the system. We are storing inside of aux cache. Aux cache. So here we are storing whatever thing. So this is something like, in that way you can consider aux cache is what? So practical, if you want to take the practical example, like imagine you are writing a story and keeping the note about your character. Some character seems minor, so you don't focus on them much initially. But as the story progresses, this character start playing the key role. So KB Caisse is like keeping the detailed notebook for main character you know will be important, and you quickly reference these token these tokens. And aux cache is what? Aux cache is like sticky notes for those minor character. Initially you don't think you would write much about them, so you didn't add them into your main notebook. But as they become become more important, instead of flipping through all your past notes, you just check these sticky notes. That's where aux cache work. Okay, aux cache and kv cache work. So hope I make you understand right, the concept of aux cache and kv cache. So aux cache, if you can consider, this is just a sticky node where we are referencing the information very frequently, and kv cache is the entire node which is about the main character. Okay, so whatever token we are removing, we are storing inside of kv cache. So any time moment of time we can get those kv cache. Okay, so yeah, so implementation detail and experiment result. And if you'll see this benchmark, I really like it. If you'll see the single document Q&A, random token drop is taking around, score is around, you can see 20.5, and TTFT means is one time faster, means randomly token drop, like randomly you are dropping. Static token pruning, in that case score is 21 point something, and speed up is around 1.18. Again, lazy LLM, the performance got improved around 20.5.59, and the speed up of your complete processing is around 1.36 faster. Similar other model called XGen, a different type of model also they tried, and they bring up this evaluation metric. Similarly, other task, multi-document Q&A, and there also we found this drastically change. The speed up is around 2.34, and score is something 22.31. So though speed up is also increasing and performance is also increasing, just applying the lazy LLM. I will come up with the implementation, like I'll integrate this lazy LLM techniques in some of the LLM in future videos. But as of now, just I walked through this research paper and I found this is very important to know about the Gen AI, like how the Gen AI can be improved, performance of Gen AI LLM can be improved. That's what I bring this research paper. And yeah, this is all about this research paper. And if you really like this research paper walkthrough, then please hit on a like button, and if you're new on the channel, do subscribe the channel so that you never miss the update. And yeah, with this, thank you guys.